We've seen that the symmetry of the harmonic oscillator potential function tells us something about the possible symmetries of its eigenfunctions, in particular that the eigenfunctions have to be either even or odd. I want to explore just very briefly in this video, where does that even or odd quality come from? So I'll once again write down the harmonic oscillator eigenstates as a normalization factor times the Hermite polynomials using scaled coordinates, e to the minus alpha squared x squared over 2. All right, so we have a Gaussian over here, Hermite polynomials, and a constant. The constant doesn't really affect the symmetry at all. This scaling constant is just mu omega over h bar. All right, let's look at this Gaussian part first. If I were to draw this Gaussian as a function centered about x equals 0, it would be a function that would look something like this. All right, now I hope that you can easily see that this function has reflection symmetry about the y-axis. In other words, whatever is happening over here is the same as what's happening over here. So we say that this has even symmetry with respect to inversion across the y-axis, or in other words, that f of x is equal to f of minus x. When you move over to the left-hand side, you're going to get the same value if you're the same distance from the origin over there. Okay, what about the Hermite polynomials? Okay, the Hermite polynomials, there's no simple formula to write them down, okay, but I've drawn the first few of them down here at the bottom. And what I've done is drawn axes where x equals 0 is right here in the middle, so you see a vertical axis that marks for you where x equals 0 is. So we're really interested in what is their bilateral symmetry. In other words, are they symmetric with respect to this vertical line, or are they anti-symmetric with respect to it? Now, in each of these cases, the harmonic oscillator potential is drawn in blue, so that it helps to calibrate you as to exactly what the extent of the Hermite polynomials are relative to the potential. Now, the first Hermite polynomial is just a constant. It's basically h0 of x is equal to 1. So it's just a constant value that goes across. It is clearly even with respect to interchange across the axis, so I'll mark that here. It is an even function, and not much more we can say about it. Okay, when we get to h of x, h1 of x, so this is h1 of x here, as labeled up here at the top, it's really just a line, and it's a line that goes to the origin because it's equal to x, or sorry, it's equal to 2x, so when x is equal to 0, the function's equal to 0. And it's just a line with positive slope of 2. Now, we can see that values that are on the right-hand side, on this side, are positive, and on this hand side, they're negative. They're, in fact, reflected across the origin. So this is a clear case of an odd function as it crosses the origin. Okay, for h of 2 of x, this is 4x squared minus 2, and we can see again that there is symmetry on either side of the vertical line. So this one is an even function, and not much more to say about that. You can see that it's a narrower parabola than the parabola that forms the potential function here. Now, when we get to the higher ones, we actually have to look at a smaller and smaller region around the center of the potential function. So that's why this one is only shown up to here, but these curves should be considered to extend beyond where they're drawn. So in this case, h3 of x, which is h8x cubed minus 16x, this one is clearly an odd function, because it changes sign when it goes to the origin. Now, one way you can easily tell is if the function goes through the origin and crosses from positive to negative, or negative to positive, then it's more likely to be an odd function. It may be neither odd or even, but it cannot be even. Okay, finally for h4 of x, we have a function here that clearly is symmetric with respect to flipping across this border, so this is an even function. And we can verify then that for the Hermite polynomials, these are even if n is even, so that means 0, 2, 4, and so forth, and they're odd if n is odd, 1, 3, 5, and so forth. Okay, and this actually is preserved, if you will, by the recursion relation. I'll remind you that the recursion relation basically says that h of n plus 1 of x is equal to 2x h sub n of x minus 2n h n minus 1 of x. Well, this is just a number, so it's a number multiplying a function which can be either even or odd. So this and this will have the same symmetry, but only if this preserves that. Well, when we multiply by x, we have converted either an odd function into an even function, or we've converted an even function into an odd function. Did I just say that? What we basically want to keep track of is if we're multiplying two functions together, so for example this Gaussian, which is an even function, if the two functions are both even, they will result in an even function. If they are both odd, that too will result in an even function. Only if one is odd and the other is even will you get an odd function as a result. So the Gaussian is always even. The prefactor here doesn't affect even and odd behavior. So in other words, the even-odd symmetry of harmonic oscillator eigenfunctions purely comes from the Hermite polynomial part of this particular formula. So I hope this has given you a little bit of insight as to where this comes from in the case of the harmonic oscillator eigenstates.